This lesson has been developed in the framework of SCILED project.
Module 3 Footwear Design Engineering Unit 2 Introduction to Materials Engineering.
Lecture 2.2 Introduction to FEA.
Introduction. The content of the static or dynamic calculation of a construction consists in determining the magnitudes of stress and strain that occur in the construction due to the action of external forces. The most common numerical methods are the finite difference method and the finite element method. The most important and widely used method today is the finite element method, which is applicable in almost all technical fields and especially in the analysis of constructions. The finite element method is a numerical technique for solving problems which are described by partial differential equations or can be formulated as functional minimization. The analysis of the original body is therefore done in 3 stages: meshing, consideration of individual elements, composition. The steps we follow in order to evaluate the strain and stress field with the finite element method are meshing, formation of stiffness matrix of each element, assembly and forming of global stiffness matrix, loading and boundary conditions, solution and evaluation of displacement field, and evaluation of strain and stress fields.
Types of finite elements. Rod elements. We use this element when modeling a mesh or grid where its elements transfer only axial forces. The element is linear and has 2 nodes. Beam elements. We use this element like a rod, but when we have a bending problem. The element is linear and has 2 nodes. 2-dimensional elements are used to model surfaces. If the surface also accepts bending forces, then we use shell elements, which are the same as the elements, but they also accept bending forces. The only data needed in 3D analysis are the elastic properties of the material. In addition to the above types of elements, several other elements are available in FEA commercial programs for more specific applications.
Material properties. In addition to the elastic properties of the materials, finite element programs allow us to determine all the behavior of the material, stress-strain diagram, or to determine different properties depending on the temperature or different properties in different directions. Boundary conditions are related to the connection of the body to the environment, and usually refer to the restriction of displacement of a part of the body. Thus, in the event of a fixed, hinged, roller or contact, we appropriately restrict the movement of the node in the position of the link. The loads in a mechanical problem can be concentrated forces, distributed forces and pressures. The concentrated forces are imposed on the nodes, the distributed on the lines and the pressures on surfaces. In addition to forces and pressures, we can also have loads throughout the body, such as temperature change and gravity.
Simplifications in the analysis with the FEM. Before we proceed to the construction of the geometry of a body, it is useful to check if it is possible to simplify the problem and therefore to minimize the computation time of the corresponding analysis. In many cases, it is possible to model a problem in 2 or even in 1 dimensions. Depending on the problem, we can have plane stress, plane strain, plane symmetry and axisymmetric models.
Modeling FEA in 2D. In case we have very thin constructions, where the thickness is very small compared to the other dimensions, we can model the problem in 2 dimensions considering that the stress in the vertical direction is 0, plane stress. In the case that we have constructions with a very large 1 dimension, for example an oil pipeline, we can model the problem in 2 dimensions considering that strain in the direction of the large dimension is 0, plane strain. In the case of plane analysis, plane stress or plane strain, we can also have symmetry with the axes. Instead of modeling the whole plate, we can only model a half, but considering symmetrical boundary conditions, that is, the displacement vertical to the lines of symmetry is 0. Axisymmetric in the case of solid by rotation. Instead of the 3-dimensional object, we can only model the surface from which it was created.
Computer-aided engineering in footwear design. Computer-aided engineering, CAE, in footwear design is used for 2 purposes. The first is performance evaluation, mechanical, thermal, comfort, etc., for an intended environment and use. The second is optimization, in which key product parameters, topological or material properties, are determined with the aim to achieve certain performance. In order to successfully apply FEA, it is of utmost importance that there are accurate geometric models of the solids of the mechanical systems under simulation, that the properties and behavior, elastic, viscoelastic, hyperelastic, of the materials are known, and that information of the operating conditions, known as boundary conditions, including loading, are as accurate as possible. The importance of accurate 3D geometric models created in modern parametric CAD platforms cannot be overestimated. The modern designer of footwear parts needs to have good skills to either create new models from concepts or to capture, reverse engineer and produce models of real products.
Optimization techniques in construction design. The purpose of optimization techniques is to search and find the best design for a construction. By setting some constraints, such as a limit on the developing stress as well as a goal, such as the minimum construction volume, we can determine the geometry of the construction that satisfies the constraints and achieves the goal. The basic principle of the technique is the analysis of the structure and the determination of the stresses in each element under each load condition. Two basic rules are used in each optimization study. First of all, we should not expect an optimization process that automatically designs the product. In addition, although optimization routines are now very accurate and efficient, we must first investigate what can actually happen with the construction, in terms of its geometry, its properties and its behavior, so that can interpret the possible result of the optimization.
Optimization phases. Each optimization study can be divided into two phases. In Phase 1, the initial ideas for the possible layout of the construction are thoroughly examined, which determines the operation, cost and production process. Phase 2 is performed using optimization study automated routines, which are provided by the specialized software. Optimization in OptShoes.
In terms of footwear, the user of the OptShoes tool can investigate the mechanical behavior of soles using two parameters: the thickness of the sole layers, the choice of materials for each layer. The designer will define a desired deformation energy density value of the sole, as it is shown in the table. After entering the thickness parameters, the OptShoes optimization module will simulate the bending behavior by using different materials, resulting in a material combination that will provide the desired comfort level to the sole.